Yes, am I audible to everyone?
Yes, sir.
Okay. So last class we were discussing about syllabus of this fluid mechanics subject, and we have discussed little bit introduction and application of this fluid mechanics, where all this fluid mechanics subject is required to apply this concepts and other things. Today I think we'll start with the syllabus, this subject introduction and other topics. So once again, coming to this first topic, we are going to discuss about fluid properties and their definitions, equations, and simple numericals we are going to discuss. So coming to the first chapter, I'll just start with the slide here. All of you are able to see the screen? Yes?
Yes, sir.
Okay. So for your reference, I have also shared this handwritten notes in the classroom. That is the Google Classroom with the first module notes, so that one can refer these notes whenever it is required. In the last class, we have discussed what is fluid mechanics. Then we have discussed a little bit different concepts of that we have discussed. Then fluid dynamics. So these are the three major parts of fluid mechanics where we are going to discuss about the fluid is in rest or in motion. So these are the three fields where when it is stagnant, we are going to call it a statics fluid. When it is having some motion without any forces, we are calling it as kinematics. And whenever the fluid is in motion with some applied forces or the external pressure is added or the internal forces are developed in the fluid, that field of application we are calling it as fluid dynamics. Is the first part. So last class we were discussing about the density and specific weight. So in these two definitions, you can just observe it is with respect to this thing you have to keep in mind. With respect to volume, what ratio you are taking is with respect to mass density or density is also called as density. Also, you can call it a specific mass. You can just observe the ratio here. Mass density is the ratio with the mass of the fluid given and the volume occupied by the given fluid. So any issue with the audio or video problem is there, just put a message in the chat box, okay? Or else you can unmute your mic and tell me the difficulties. If any problems are there with the audio. Okay. Screen is visible, right?
Yes, sir.
All of you can see the screen. Okay. So coming to the first definition, mass density is nothing but the mass of the fluid in a container and volume occupied by the same fluid or the given fluid. So that we are taking it as kg per meter cube. So whenever kg per meter cube is there, it is nothing but the mass density. And here, if you take the water as standard liquid in this example, so if you put the water uh, breadth and width is 1 meter. So such container if you take and fill it completely with the water. So mass will be how much? It will be 1000 kg for the meter cube of volume. That is called as mass density or normally density. Volume varies. In the sense, volume you can vary only by applying some pressure or a temperature. I hope everyone will agree for this. whenever you go on increasing for any given liquid or solid, little volume will go on increasing. So in such cases, volume also increases. In the sense, if you assume the container is completely closed, in such case, the pressure may be increased or decreased, whatever. If pressure is increased, you know that I'm applying the force on the entire fluid part, and volume is going to little bit reduce. In such case, the density is going to increase, but not for the water.
Excuse me, sir. Hello?
Hello?
Sir, we are facing audio issues in the middle.
Okay, just a minute.
Sir, I think it is mainly because of network problem.
Yeah, now it is clear. Now audio is clear.
Yes, sir.
Okay. So all of you know that when you increase the pressure on any volume of the liquid or the gaseous, this one, what will happen? The density is going to increase as the volume decreases. So volume I am going to decrease by the increase in the pressure. So that part you have to just observe here. So that is I have written here. Just the upper arrow mark indicates pressure is increasing. When pressure increases on any gas, volume is going to decrease. So as volume decreases, what happens? The molecules of the gaseous thing will be coming together, and it is going to increase the density. So here, change in pressure, we are going to mostly talking about the gases, and change in temperature with respect to temperature. If you take the oil or water, it is very difficult to compress. So those liquid type of fluids, we are calling it as incompressible fluids. We cannot compress easily. And gaseous objects, if you take, those are compressible fluids. So fluid is the topic where we are discussing about both liquid as well as gaseous states. I hope this definition is clear to everyone. Mass density or a specific density.
Yes, sir.
Okay, you can note down this ratio and the unit, SI unit. And for the standard water also you can note down 1000 kg per meter cube. The next definition is the specific weight or the weight density. Now by the name itself you can understand weight density means we are measuring the density with respect to weight as a component, not by the mass. So mass and weight relation, you know, if I multiply the mass with gravitational force, it will become weight of the given body. So specific weight is the ratio of weight to the given volume of the liquid or volume occupied by that liquid. So sometimes to confuse, they may ask with the specific weight also. Is that clear? If they tell weight density, everyone knows that you have to take the ratio with weight and the density, this volume. But to confuse what they tell, specific weight they may tell. So here what you have to do is specific meter cube, and weight is also written here. You have to take the ratio with respect to weight, and it is denoted by small w or gamma. So these are the two words here, w or gamma. It is denoted. And coming to the conversions from the density or the mass density, if you see that was density, rho here indicated as rho, multiply with this gravitational force. So once you multiply density with g, it will become specific weight. Is that clear? So here, so entire equation, if you see, it should be either density into g, or it should be mass into g divided by volume. So you can write both the equations. You can write density into g, only one term separately. Here I have written mixed. Okay. Next equation is what? For specific weight or mass, it should be m into g. m into g will be w, that is weight of the given fluid. Then the w per unit volume, if you take, it will become specific weight. So here for the water we were discussing as a standard liquid. For water, if you take, it will be 1000 kg per meter cube was density, mass density, 1000 kg per meter cube. What we are doing, we are just multiplying with 9.81. So that will become 9810 mass. All of you know, for a given meter cube, what is the mass? 1000. And to convert this kg into Newton, what we have to do is we have to multiply by 9.81. Means 1000 is already in kg per meter cube. Just we have to multiply with 9.81. This will become Newton per meter cube. So just note down these points: ratio and the values of the standard liquid as water. Yes, Prajwal Joke, is it understood to you? What is specific density and specific weight? Okay. Please, everyone, note down these definitions and the ratios. That will be practice for yourself. You can also practice and you can check the units also. So what is the unit of weight? This Newton. Can you tell me, anyone? Unit of Newton, if you expand it, how you can define Newton in kg?
kg meter per second square, sir.
Yes.
kg meter per second square.
Yes, very good. Kg meter per second square is the other unit of Newton. Okay, going to the next definition, specific volume. So specific volume is shown with small v. It is not gamma. It is a small v. Specific volume. This is nothing but the reciprocal. Okay. Or if you define, it will be ratio of volume of the fluid per unit weight. So per unit weight means what is this? It is nothing but the ratio of or the reciprocal of specific weight or the weight density. Is that clear? If I take the reciprocal of weight density or the specific weight, meter cube per Newton, what you said now, Newton per meter cube, that ratio, if I reverse it, that will become the specific volume. The meaning is, again, it is for per unit per Newton, how much volume is occupied, or per unit volume, how much was the weight acting in newtons. So that reciprocal, if I take, it will become small v equal to meter cube per Newton. And here I have also written what is the specific weight, Newton per meter cube, that we have discussed. Now what will be the value of this small v for the water? It should be 1 by 9810 meter cube per Newton. Just reciprocal of that value, 9810, what I have written, that you have to take 1 by 9810, and units also will change. That will be meter cube per Newton. So this is the definition of specific volume. It is the ratio of volume occupied by the given fluid per unit weight. Okay, next definition is specific gravity. So here what we are doing is, so until now we have discussed for the one fluid and taking the example of water, how the density value is going to change, how the specific weight is different, and how you are taking the specific volume for a given one of the fluid. Now if you want to compare two fluids, in such cases what we are going to do is, we are going to take this specific gravity as a reference. Specific gravity is nothing but measuring the density of any fluid with respect to the standard fluid. So in applications, many liquids we are using. So in such cases, you have to tell the specific gravity or the relative density. The meaning is, the background meaning is, how much is the density, whether it is higher than the standard fluid or the density of the given liquid is lower than the standard fluid. That we want to discuss. So here there are no units because both ratios are in the same units. There will be no units for the specific gravity or the relative density. So specific gravity is denoted by S here, small letter S. And ratio, if you see, it is the mass density of fluid, means mass density of the given fluid, which is used in the applications. Maybe oil, you can assume it as a oil, mass density of the oil, to the mass density of the water. Why water here? Because water we are considering for almost all examples in the fluid mechanics as the value is compared with the water. That's why I have taken the ratio here, mass density of fluid, any fluid with the reference or a given applied fluid, to the mass density of the water. So these two things if you take, it will give you density of the fluid to the density of water. Both units will be get cancelled. That is kg per meter cube divided by kg per meter cube of the water. So both units will get cancelled. There will be no unit. It will be only one number. If that number is below 1, meaning is what? The density of the given fluid is less than standard liquid. If the value of specific gravity is more than 1, or the relative density value is more than 1, that indicates the density of the given oil is more than the water. I hope this point is clear. Or also you can take that specific weight also, or the weight density also, both are same. You can take the specific gravity ratio as, I'll just once again read it in a different form. Specific gravity can be written as ratio of weight density of the given fluid to the weight density of the standard fluid, water. Both will give you same answer. You can take either mass density or the weight density. Is that clear? Yes, Sunil, have understood the definitions?
Yes, sir.
Okay, Vinayak K.
Yes, sir.
Have understood the definitions?
Yes, sir.
All these definitions have you
Understood, sir. Okay,
Okay.
sir.
Are you noting down the
Understood.
definitions and units?
Yes, sir. I'm noting down, sir.
Okay. Yeah. Because what happens here in the properties, we have all the ratios and units and conversions, notations are there. It may get confused later. So better you note down in a.
Okay, sir. So we are all noting down, sir.
Okay, now we take one problem here. All of you note down this problem. I'll just read once again here. Specific gravity of a liquid. Now see here, before understanding what is there in the problem, you understand the words. In the problem, they are mentioning specific gravity. So what you have to do is, first step only you have to write down the specific gravity relation. What is specific gravity? I can write it is mass density of the given liquid to the mass density of the standard liquid. Or can write specific weight of the given fluid to the specific density. Sorry, what is that? Weight density of the given fluid to the weight density of the standard liquid water. That as a definition or the relation I can note down first. So here specific gravity of a liquid is 0.7 is given. Means S value is given. Specific gravity S value is given as shown in the above formula. That S value is given in the problem. Okay. If S value is given, just without questions, just see the relation above. Mass density of the water is also known to us. So mass density of the water is what? 1000 kg per meter cube. Everyone knows it. That I can substitute. I know S value as 0.7. Without asking question, I can find out mass density of the fluid. I hope the point is clear. Now we'll see the question, what they are asking. So first they are asking again same thing, mass density of the given liquid of specific gravity 0.7. Second question is specific weight of the given fluid. Okay, that we need to find out. Then we need to find out also the mass and weight of 10 liters of the liquid. And in bracket they have written that liquid is petrol. So using this data given in the question and noting down these all questions, what is that? Mass density we need to find out for the given fluid. Specific weight we need to find out. Then we need to find out mass and weight separately of for 10 liters of that liquid. That liquid in bracket what they have given, petrol, for the reference. Now again recall all the ratios. So as I told you, for the first case, mass density we need to find out. I'll write S equal to S mass density by mass density of water. That I'll write. So here we know that mass density for the water is how much? How much is the mass density?
1000 kg per meter.
Yes, that you have to substitute and find the mass density for petrol. To substitute in this equation, find mass density of fluid. 1000 into 0.7.
700 kg per meter cube.
How much you are getting? Yes. 700.
700 kg per meter cube.
Yes, very good. That first question is what? That is mass density. Next is they're asking specific weight. Specific weight, what is the unit? Specific weight, Newton per meter cube. Yes or no? That we have discussed here. Specific weight. The unit is Newton per meter cube. So convert that into Newton per meter cube. So to convert that for the given petrol as a liquid, what I will do is 700 into 9.81. That I can do. 9.1 into 700. Or else what I can do is in the specific gravity equation itself. I will write this equation as weight density of the given fluid to the weight density of the water. In this case, one should know what is weight density of the water. That we have discussed, weight density in Newton per meter cube is 9810. From this also you can find out the weight density of the given petrol. How much you are getting? You can find out the values in any way.
Hello, sir.
How much is
Hello,
the
sir.
value?
Can you repeat this? Can you repeat this? Okay, sir.
Yes. See, I hope density is clear to everyone. Mass density of the petrol.
Yes, sir.
Okay, now coming to the specific weight. So specific weight, what I'll do here is the equation what is known for us, specific weight, is nothing but the density into G value. So only thing here, the equation is wrong here. What you have to do is, this should be only density into gravity. Or else you have to take weight by volume. So that weight by volume becomes specific weight. Now already you know the density of the petrol. How much is the density of the petrol? Is 700 kg per meter cube. Already you have found out. So for that, what I will do is I will multiply just with the 9.81 gravitational force meter per second square. If I multiply, you have to get how much? 6867 Newton per meter cube. This is the one of the way. One of the way you can find out specific weight of the petrol. Another way is you know the specific weight or the weight density of the water. Yes, that weight density or the specific weight of water is how much? 9810 as a standard value. See here, gamma standard is in the numerator in the first equation. Gamma standard is what? Weight density of the water. 9810 is in the denominator. This I will multiply with specific gravity of the petrol, 0.7. If I multiply, how much will be the answer? Means that is gamma of the given fluid. Means it is weight density of the petrol or the specific weight of the petrol. That I should get 6867 Newton per meter cube. You check the value, is it correct?
Yes, sir.
Yes.
Yes, sir.
I think all of you understood both the steps.
Yes, sir.
Okay. So next what they're asking in the question, you just see. Specific weight is over. Now we need to find out mass and weight as separate entities for the given liquid as petrol for 10 liters. So for that, what here we have done is that liter we need to convert into meter cube. Okay, so 10 liters in meter cube will be how much? 10 liters we need to find out. So either it may be a water or petrol, the volume occupied by that 10 liters. That we need to find out first. That is nothing but 10 into 10 raised to minus 3 in meter cubes, because in all the equations we are using the units as meter cube for the volume, not liters. Is that clear? So that contained in the container. Now we need to find out the mass. So already we know the density equation. The density is nothing but the mass per unit volume. So mass per unit volume, what are the units? Kg per meter cube. Correct. So meter cube we know. Kg we need to find out. Why? Because the question is find out the weight and mass of the petrol is asked. So you read the equations of density and weight for petrol in terms of petrol and substitute the volume of the petrol here. So now I can find out the mass as mass equal to what? Density into volume. So from the relation of density, we know that mass can be found out by multiplying volume and density. So that density is how much? Density is 700 kg per meter cube, already we have found out. Then we need to find out 10 liters of oil, and for meter cube you have to again multiply with 10 raised to minus 3. So by that one can find out mass. Are you getting 7 kgs?
Yes, sir.
Okay. Last question is what? We need to find out weight of the petrol. See here, weight of the petrol which is occupied in 10 liters. So that weight we have to find out. Just multiply mass with 9.8 by the definitions. So go by the definitions means you go by weight density. So if I go by weight density, the ratio is, what is that ratio? Yes. So specific weight, we know that weight of the given fluid to the volume, or else I can go by this mass into gravitational force directly. Both answers you have to get same. One by general method. The weight of our body is how much? Mass into gravitational force. That is our weight. Then mass, if you want to find out of the given body, what to do is you have to divide weight by gravitational force. That becomes mass of the body. So just practice it on the paper. Have you done that problem?
Yes, sir.
Is audio is clear now? Voice is clear? Okay, is the solution you got?
Yes, sir.
How much is the answer? Weight of the petrol for 10 liters. How much you got?
68.67 newtons.
68.67 newtons. Say one more thing. Here Newton is written because it is weight, not the mass. That's why just if you convert kg into Newton, that will also become weight only. So what I'll do here is one more method. I'll take 7 kgs. 7 kg I'll multiply by 9.81. One and the same. Or else you can multiply with this specific weight into volume. Okay, I hope this point is clear. So take one more problem here. Just note down the problem and solve it. Yes. All of you note down. Calculate specific weight. Calculate specific weight, mass density, specific weight or weight density. Calculate weight density, mass density, specific volume, and specific gravity of a liquid. Of a liquid means whatever the definitions we have discussed now, 4 definitions, on that only problem is there. Of a liquid having volume of 4 meter cube. So volume is given in meter cube, no need to worry about this. Directly you have to substitute 4 meter cube and weighs 29.43 kilonewton. This is the weight given in kilonewtons. Means you have to take 29.43 into 10 raised to 3 newtons. And one note is given here, assume missing data. Assume means you have to assume for the standard liquid. Whenever you take the ratios for standard liquid water, we need to assume, as we have assumed in the last problem. So try to solve this problem for finding specific weight, mass density, specific volume, and specific gravity. The given values are just 4 meter cube, 29.43 into 10 raised to 3 newtons. Okay. Yes, sir. Okay, anyone solve the problem? Follow the same method of last problem. No need to convert liter into meter cube also. Directly meter cube value is given. Weight is also given kilonewton. Yes, one answer is there. Varsha Joshi has given 7357.5 Newton per meter cube. Yes, very good. We'll see that. Okay, 7357. Okay. So once you find out the weight density or specific weight, Newton per meter cube, you can also find out the mass, weight, from the density. And density also can check here. Again, as for this last problem, they have solved in two ways. One is weight density. We know that we need to multiply density with gravitational force. We'll get the weight density. That is 7357.58 into 9.81. If you multiply, I'll get 750 kg per meter cube. This is one of the answer, one of the way. One more way is we know the density definition. Density definition is what? Mass per unit volume occupied by the fluid. So that mass is how much we are getting here. Mass is around 3000 kgs as per the above relation, and volume is already given in meter cube, 4 meter cube. So if I take that ratio, I'll get same 750 kg per meter cube. Yes, up to density, is it clear?
Yes, sir.
Mass, density, weight, and weight density. These results, how to get, all of you understood? Okay. The next part is they're asking specific volume. So specific volume we have discussed, volume of the given fluid to the mass, or it is nothing but the reciprocal of mass density. Mass by volume, what you have taken, that reciprocal you have to take. So mass density reciprocal, if I take, I can take 4 by 4 meter cube by 3000 kg per kgs or kg per meter cube, or else also I can write 1 divided by 750. So one of you check reciprocal of that density, 1 by 750. Are you getting 1.33 into 10 raised to minus 3 meter cube per kg? 1 divided by 750. Yes, Srinivas has shown values, Pushpa has shown, Anish Chaudhary, he is telling yes. Okay. So 1 by 750 also 1.33 here. At the bottom you can see here 1.33 into 10 raised to minus 3 meter cube per kg. That is the specific volume. Means for meter cube volume given and the mass of the given fluid. Next is the, you can find out the specific gravity or the relative density, the last part. This also you can find out in two ways. Both ways you have to find out the ratios. What ratios? Either you can go for specific weight or the weight density ratios of given fluid to the standard fluid water, or one more method is you can go by density ratios. That is mass density of the given liquid to the mass density of water. So both values of water we know. This is the assumption. What is our assumption? What is the weight density of water? 9810. What is the mass density of water? 1000. These two assumptions, why we are doing is, these two values are the standard values. So once you take these two values, so one can find out either in with respect to the weight density ratios or in the mass density ratios. Both answers are same. Just check all of you. Yes.
Yes, sir. Yes, sir.
Yes, are you calculating? Zeba? Zeba Tangsali? Okay, Anish Chowdhury answer you got 0.75. Zeba is not attentive, I think, for the class. Sunita?
Yes, sir.
Yes, yes, what is your answer?
I got
Okay, sentence
7.35, sir.
following. Okay. Okar, Khalid, all are getting answers. Very good. Okay, coming back to again this problem. So such type of problem, why I have taken multiple ways of calculation, or why I am finding this all answers in the different ways, because the problem can be asked in many ways. Okay. Sometimes they may ask for the water itself. So in that case, can you tell me what may be the specific gravity of the water? Can reply in the chat box.
It will be 1, sir.
Specific gravity of the water, I want to find out. Yes, very good. Rashmi has given the answer 1. Why? Because I'm taking the weight density ratios of water to water, or else I'm taking the density ratios of water to water, one and the same. So the specific gravity of water will remain 1. That is also a standard value. So in any form of the problem given, you should know the relations and the units are proper. One can find out the solution in any of the ways, one or the other ways. So I hope all the properties and the numerical is clear to everyone. So I think we'll stop at this point for the first class. It's already now 12:43. Next class again will start at 1 p.m. Okay, so I'll switch off here. So just recall all the definitions once again. Those who have not attentive for the class or not solve this problem properly can look at the doubts what you had, units conversions. Please carefully observe the problem once again. So next class will start with the vapor pressure, other properties. Okay. Yes, shall we continue?
Excuse me, sir.
Yes.
Sir, what is specific volume?
Yeah, that was I was explaining. What's your name?
Yes, sir.
Okay.
So specific volume is nothing but reciprocal of specific weight.
That's what boss. Yeah, coming to the next class. So one of the student, yes, is asking specific volume. The last problem numerical we have taken. What is that? Meter cube per kg. Am I right? Means with respect to mass we have taken, not with the weight. All of you check the answer. Yes, correct. So here I will once again explain it. Specific volume. See, as per the definition of specific volume, if you see, it is the ratio of what? It is the ratio of volume per unit weight. Is the actual definition. But in the problems, if you see, we have written the answer in specific volume. See, small v it is here. This answer we have written 1.33 into 10 raised to minus 3 meter cube per kg. So as per unit, the answer is correct. Now, as per the definition, if you go, you can also take volume by weight. So I think you also write the one more note there at the bottom in the problem. You can write the note. Specific volume is take the ratio now volume by weight and check the answer. But here what will happen? Units will change now. Units will be what? Meter cube per Newton. Or what you do here itself, you take 4 divided by 3000. 3000 you multiply with 9.1. That will become meter cube per Newton. Both answers will be considered as per the units. If you write 1.33 into 10 raised to minus 3 meter cube per Newton, answer is wrong. Because as per the definition, you have written the units correct, but the answer is in meter cube per kg. I hope the point is clear. Yes. You can write
Yes, sir.
answer as meter cube per Newton or meter cube per kg, but the conversion should be clear. Yes.
Yes, sir.
Okay. I think your doubt is correct because in definition we are telling volume per weight. Yes or no? But that's why
Yes, sir.
in the units I have not written newtons. Meter cube per Newton I have not written because as per unit it is different. So if you want as per definition units only meter cube per Newton itself, so just multiply this 3000 by 9.1. You will get meter cube per Newton. So writing the units is very important. Answer as per this unit is correct, no doubt. So that's why one more step you add. Write it as specific volume is ratio of volume by weight. Then what you do? 4 divided by 3000 into 9.1. What is the answer? You put in chat box. How much you may be getting? Mohit Baig, put the answer in chat box. See, many are not attentive to the class. Mohit, not attentive. Okay, I'll continue. Can you put the message in chat box? Any doubts up to here? Yeah, answer he is getting 1.359. Chandan, 1.359 into 10 raised to minus 4. This value is in meter cube per Newton, I think. Yes. Ashish is also telling same answer. 1.359 into 10 raised to minus 4. Yes. So I think this problem is clear. You can write in any form. Unit should be clear, or as per the definition, that unit should be correct. So either you go by definition or by the units, whatever, that as per units the answer should match. Okay, still Mohit is busy in his own work. Mohit, I'll put absent Mohit Babe. Okay, coming to the next part. Recording. Yes. Yeah, moving to the next definition or next property of the fluid is vapor pressure. So here talking about the vapor pressure, as all of you know it, I can prepare the vapors of water by two ways. One is already you have to boil the water or any liquid up to its boiling point, or you have to cross the boiling point. Then the vaporization or the evaporation starts. One more is at the same temperature, as you might have seen in the nature, at same temperature or the very low pressures, what will happen? The surface of the water starts vaporizing, and it will prepare some fog or some vapor from the surface. So that you might have observed in the morning time. What will happen? The water or the liquid in the lakes are at hot temperature, and the surrounding conditions or the temperatures are very less, or pressure may be less. So in such situations, what will happen? Either by high temperature or by the low pressures, liquid starts evaporating, and with the high temperature moving wind also. That high temperature moving wind also carries the vapors of the water surface or the liquid surface, and this minimum pressure which is required to vaporize any fluid, because we have to talk about here not the standard water itself. So any fluid if you take, it requires some pressure or the minimum pressure at which the vapors on the surface starts emerging. That minimum pressure we are going to call it as vapor pressure. So if you increase the temperature of water, because water we know the values. So for the water, if you consider as an example, if you go on heating it at atmospheric pressure around 100 degrees centigrade, it will start boiling and it will start giving the vapors. But if you might have seen also even at low temperatures and at a localized high temperatures of water molecules. If you see, before boiling temperature also, a little amount of vapors are emerging outside. So that locally, if you check the temperature and pressure, it may be slightly different, due to which what will happen, vapors are formed on the surface. So this minimum vapor pressure or the pressure required to vaporize the fluid, we are calling it as vapor pressure. And the process of this vaporization of any liquid, we are calling it as vaporization process. Is that clear? Or you can take the example of this one. As I told you, the lake water is going to evaporate slowly, and that vapors you can see from the naked eyes. So what will happen there? Water may be in the cold condition, but what will happen? The land which is connected to the water, it may be in the hot condition. Or the surface of the wind, what is connecting with the water surface, may be at the higher temperature. Or it is increasing the temperature on the surface of lake. So in that time also, when the temperature difference is there, or any pressure difference is there on the surface of liquid, that also little bit it will start evaporating stage by stage. So that vaporization locally, I'm talking about locally because not that complete surface of the liquid only evaporates as a surface. It may also evaporate by a locally, whatever the molecule is acquiring the higher temperature or the lower pressure, whatever, that locally also at a given point, the liquid may vaporize. So this process is vaporization, and the minimum pressure or the temperature required to vaporize this liquid is called as vapor pressure. And this is measured in Newton per meter square. As I told you, minimum pressure is what? Pressure is force applied per unit area. So here I have taken force as Newton per unit area, means that surface area meter square. So this minimum pressure required is nothing but the minimum force per unit area required. So that minimum force per unit area is Newton per meter square, which is the unit of vapor pressure. So all of you can note down this unit of vapor pressure. Vapor pressure point is clear? So this vapor pressure, why we need to study is, whenever in the enclosed channels, when the fluid is flowing, suddenly the vapors at high temperatures may start evaporating. So in such situations, what will happen in the chemical industries or in the steam power plants, in water pipelines itself, we have the liquid as well as the gas flowing. And these gas and the liquid, what is mixed in the flow, this may start cavitation process. Cavitation means it will start preparing some vacuum or high pressure regions because of the gas formation. Because when liquid is flowing, the mass may be high in the pipelines, but the pressure may be less in the fluid, in the pipeline. But whenever the liquid transforms from liquid to vapor, all of you know that volume will increase. So as this volume increases from liquid to vapor form in a given enclosed channel of pipelines or any containers, indirectly the pressure of the container or the pipelines will increase. So this pressure will lead to suddenly bursting of the pipelines or creating some cavities in the pipelines or the containers, so that we don't have complete flow or the complete filled flow we don't attempt. So this may be the one of the problem of cavitation. So one need to maintain the proper low temperature or the pressure, so that vaporization or the vapor pressure should not exist in the given liquid surfaces. This is one thing. One more thing, if you see, normally when we don't change the temperatures or the pressures, in such situations, in the pumps, if you can see, or in the turbines you can see, or in the in a simple bucket in our home filled by taps, You might have seen in those examples. So in such situations, what will happen when the pumping of water or the flowing of water takes place from tap to bucket? You might have seen small bubbles will be formed when water is mixing continuously with the tap water. Small bubbles will be formed, and those will be bursting at the surface. So in the chat box, just tell me, have you seen that process? Or put a little bit soap or detergent in the bucket, start filling the water by the tap with some force. What will happen at the surface? Small bubbles will form, or the bubbles of soap will form, and it will burst at the surface. So similar process when it is high pressurized fluid like steam or water at normal temperatures or the working temperatures or the we can call design temperatures, because pump is designed for the normal temperature. Turbines are designed for the high temperatures. So at given condition, when the steam is flowing or the high pressurized water is flowing in the pump with not filled flow or complete flow, or when the tap water is filling in the buckets, so this bubble formation will start because of the low pressure at a given points, and these bubbles will suddenly burst at the surfaces of the pipe or enclosed impeller channel of the pump, or between the enclosed channel and the turbine flow. These bubbles will start bursting, even in the buckets also, or in the containers. So whatever the system you can consider in enclosed channels, this bursting of the bubbles will start eating up the materials for a long duration of time. The life of the material will reduce because of this eating or the pitting action. So as these bubbles will start bursting at high pressures, the surface of the pipe inside will start eroding. So for a given long time, this pipe inside surface will start eating up by these bubbles, and small amount of metal or the material of the pipe will be carried away through the flow of water. So this action is again different, which is taking place at given conditions, not at the very high temperatures or pressures. This type of phenomena is called as pitting action, or can remember it as the bubbles which are bursting out, it will start eating the material. So eating is nothing but pitting here in the fluid mechanics. So these two phenomena are very important, or it may also completely stop the plant operations, or it may burst the pipes at a sudden given points without knowing anything. So in such situation, in chemical industries or the power plant industries, one should maintain the low vapor pressure points or the high vapor pressure points. Means it should not be beyond the vapor pressure point, so that there should not be any mixed flows to create the cavities in between, and due to these cavities the bubble formation will be there, and at high pressure, after bursting these bubbles, the surface of the material will get eroded, or the smoothness of the surface will reduce. So this is the importance of this vapor pressure formation. So now we'll take one small example or a numerical. You can note down here. So this numerical you can just observe here. I'll read the complete question. A vertical cylinder of 300 mm diameter is fitted at the top with a sealed but frictionless piston. Means what they have given, vertical cylinder is there of 300 mm diameter is fitted at the top with a sealed but frictionless piston at the bottom, maybe bottom or horizontal, whatever you can consider. A piston is fixed like that, where it is frictionless. Frictionless is an assumption, it's not possible. So they are telling frictionless, and it is sealed. Sealed means there is no possibility of leakage of the liquid from the piston cylinder to the atmosphere or the outside. And is filled with water. So directly standard assumptions we can do. It is filled with water at 70 degrees centigrade. So temperature is given, the value you have to note down. 100 mm diameter cylinder. Inside values are known now. The piston is exposed to atmospheric pressure. So atmospheric pressure they only have given. We need not have to assume it. Atmospheric pressure is acting on the other side of the piston. One more side inside piston, water is there. It is applied by the atmospheric pressure. How much? 101.3 kilopascal is given there. In this, we need to calculate minimum force required to cause water to boil or vaporize. See the question here, they are not telling to boil it. What we need, whether it will vaporize or not, only that we need to check. So calculate the minimum force or minimum pressure, because pressure if I tell it is force per unit area. If I tell force, it is the Newton, directly applied force for the given point. Force required to cause water to boil or vaporize at above temperature, and vapor pressure is, see here, at above, vaporize at above temperature from 70 degrees centigrade. Vapor pressure of this water in that cylinder piston arrangement they have given 32 kilopascal. So now we'll discuss what is Pascal, what is kilopascal, whatever it is. We'll discuss in the given solution. Shall I do it once again? So piston cylinder arrangement is given here as per sketch. So all of you look in the sketch here. Piston cylinder is given. Diameter of the inside cylinder is 300 mm. It's given here. Temperature of the water inside the cylinder and piston is 70 degrees centigrade. The pressure applied by the atmosphere, this P is shown across the piston throughout the surface of the piston, is nothing but pressure, Newton per meter square. That is 101.3 kilopascal. So later we'll see the conversion. And here the vapor pressure means at this temperature or above temperature, they are telling, they don't know. But the vapor pressure is how much? 32 kilopascal. At this point, water starts emitting the vapors on the surface of the liquid. See here, now to reduce the pressure from 101.3 to 32, because what they are telling, at 32 kilopascal pressure only the vapors will start emitting. So earlier in the normal condition, piston was acted by an atmospheric condition. This atmospheric pressure we need to disturb, or we have to reduce or increase such that the water should start emitting vapors. Means what you have to do now, from 101.3 to 32 kilopascal, both units are same, means we need to reduce the pressure in this phenomena. So to reduce the pressure, how much we have to reduce? That they have given here, 101.3 minus 32, simple. The difference will be 69.3 kilopascal. Pascal is how much? Newton per meter square. I hope this point is clear. Means we have to create the pressure difference of 69.3 kilonewton per meter square. This step is clear. Why they have taken the difference? Anyone can answer yes in the chat box. Yes, which topic I have to repeat, Pushpa? Problem or complete theory? Okay, only about the difference. Okay, okay. Just a minute. See, in the problem they are telling, this piston cylinder arrangement is kept in atmosphere. Inside piston cylinder arrangement, water at 70 degrees centigrade is kept. This point is clear, I hope. Now, after this, what we need to do is, we need to create vapors of this water, keeping the piston cylinder with the same temperature of 70 degrees centigrade. We need to create some vapors. In such situation, as per the given problem here, we need to decrease the pressure acting on the water. Means that atmospheric pressure or whatever the piston is freely kept as it is without movement. This piston I have to move downwards or upwards to reduce the pressure, so that inside the piston cylinder some vapors of the water can be formed. Now can you tell me the answer whether I have to lift this piston upside so that the water pressure is reduced, or I have to push the piston downside? So just give me the reply. Yes, Pushpa is telling you have to move upside so that pressure in the water will be reduced. You got to lift upside. Very good. So we have to lift this. Means in the second case, what I have to do? I have to show this pressure of the force in the opposite direction, so that whatever the pressure earlier it was present, it will reduce. I have to reduce until what point? I have to reduce up to 32 kilopascal, because at that point it starts vaporizing. Still more, if you move upside, more pressure reduction will be possible, so that more vapors may be formed. But our requirement is what? Minimum pressure required. So that what difference of pressure we have to lift? We have to lift, no? So as you are telling, you have to move the piston upside or lift. At what force you have to lift? At what pressure you have to lift? To find that, we are using the difference. So earlier, without touching that piston, it was 101.3, nothing but atmosphere. Atmosphere is always applying the pressure on us. 101.3 kilopascal, wherever you go. Now, if I apply some low pressure or try to lift it, okay, and I have to attain 32 kilopascal. So if I take the difference, I will get to know that what is the pressure or force required to lift it. That's why they are taking the difference from the given problem. So I hope why the difference is taken is clear to everyone. Okay. So once the difference is taken, we found that difference is means at what force or pressure I have to lift is 69.3 kilonewton per meter square. Whenever I talk kilonewton per meter square is nothing but kilopascal, or at that pressure. Why pressure? Because it is per meter square. It is not only newtons. Newtons means force, point force. But here if I tell kilonewton per meter square, it is a pressure. At that pressure I have to lift the piston. Once I lift that piston by 69.3 kilonewton per meter square, it will move up to some distance, and after that moving of the piston at a given force, it will stop, and vapors of the water will be created at the inside the piston cylinder arrangement. So this pressure we got to know. Now we will find out force, because in the question they are asking what is the minimum force, or the calculate the minimum force required, not the pressure. Pressure you know. Now you will find out the force. So pressure I told you earlier, it is a force per unit area. I have written here force per unit area. Now in this relation P equal to F by A, we need to find out force. What you have to do? Force equal to pressure into area. So in the problem, actually speaking, actual applications, the piston area and the cylinder area will be little bit different. There will be difference. But in this theoretical problems, we can assume piston area and the cylinder area both are one and the same, without any piston rings or without any small gap. Is that clear? So theoretically, in such piston cylinder arrangements in numericals, theoretically we are assuming piston area is equal to cylindrical inside area, because piston is moving inside. So here piston area, if I consider, why I am taking piston area actually, because the force is applied on the piston only. We cannot apply force on the cylinder. If you apply the force on cylinder, cylinder is completely rigid. It is not moving. Piston is moving. So area of the piston, if I take, which is in contact with the water here, the piston which is in contact with the atmosphere, if you take, it is having rod. So we need to neglect their piston area and the rod area. But here water contact piston, if you see, it is having complete diameter as a circular surface. So that inside diameter is given 300 mm of cylinder inside diameter. Same diameter I'll consider here. So we know pressure 69.3 kilonewton per meter square into area of the circular surface. So whenever circle comes, we know that area we can write it as pi by 4 d square. Pi by 4 is written, diameter is in meters they have taken. So in the problem, diameter what they have given, 300 mm they have given. So write it in meters, 0.3 meter square. So force you can find out around 5 kilonewtons or 4.9 kilonewtons is the force required to lift the piston. Once you apply that force, it will reach 32 kilopascal. Water vaporization starts at 70 degrees centigrade inside the piston cylinder. So this problem I have taken to understand vapor pressure, how to attain. In this vapor pressure concept, how the force and pressure will act. All of you understood now? Okay, just go through the steps again. The normal pressure without vaporization is 101.3. Pressure required to achieve vaporization is 32 kilopascal. So because of these two pressure difference, how much at what pressure we need to lift the piston? That's why they have taken the difference 69.3. So that value was the pressure. Now from the pressure one can find out force. Okay. Any doubts in this problem? All of you understood? Yes, Santosh Kumar Deshpande not understood. You can replay the video later. Video is already saved here. I will share this video. In the video I have explained 3 times. That video you can replay for any number of times. I have no doubts. No sir, no doubts. Okay, thank you. I thought you are not understood. That's why you put the message clearly. Yes means what, no means what. Yes, even previous one. Previous one what? Understood? Pushpa? Yeah, pressure, force by area, correct. Yeah, previous class record you didn't get or got it? Okay, today I'll share that last class, both videos I have sent in the stream. You go to the classroom, Google Classroom. Just a minute. Anyhow, I am sharing the screen here. I'll show the videos what I have shared here. So go to the stream here in Fluid Mechanics 18AE33 stream. In this stream, I have shared both these videos here. Class 1, there I have explained the syllabus. And second class, I have explained about the basics of the fluid mechanics and applications. Here in this class, if you click that stream link, this is the second class where I have explained all these applications of the FM. These two are shared in the stream. You have to go to the classroom. Yeah, F into area is for, no, 1 minute. See here, pressure is what? Force by area. Okay, force acting per unit area. Now from this relation, we need to find out force. So what will be the change in equation? Force means you have to multiply pressure into area. For pressure, we are taking ratio of force by area. For force, we are multiplying pressure with area. It's clear. And answer is 4.9 kilonewton. Yes, Vinay Keri. Yeah, you can note down this problem. If you are doubting it, you can note down the steps. Anyhow, you have taken the module 1 notes. Still, if you have doubts, you can just note down this difference, how they have taken from the pressure, how they have found out the force. I'll give 1 minute, you can note down this problem. Okay, already noted down. All of you noted down, others? Okay. Next concept is, we'll repeat in this next class also, but before going to next class, we'll just understand what is Newton's law of viscosity. It's very important. Later, using this same theory, we are also differentiating different fluids. Either they are behaving like Newtonian fluid or non-Newtonian fluid. So whichever the fluid obeys this Newton's law of viscosity, we call those liquids as Newtonian fluid or Newtonian liquid. And whichever the liquids don't follow the Newton's law of viscosity, those fluids we are calling it as non-Newtonian fluid. Now, how to decide whether it is a Newtonian fluid or not? For that, we have one equation. So that fluid should obey that proportionality or the relation between the viscosity and the other parameters. Now here in this example, I have taken, so same 2D sketch I will show in the 3D sketch, the PPT here. Yes. In this top side figure, you can see there is a fixed plate on which a liquid is flowing. So assume liquid is a water. Water is flowing. Above that, one more plate is kept. This is a just experiment. Just above that, one more plate is moving in right side direction. And both surfaces are having some contact area, that is capital A is shown. And the force by which the plate is moving, only the above plate is moving, bottom plate is kept stagnant. Just to understand how the fluid will behave. And the difference between these two plates are maintained at a distance of y. Capital Y is shown, or at a distance of any value you can take. It is in y direction, they have taken y. So in the right side direction, if you see, if I move this plate by some distance u, the layer which is connected to this moving plate, the layer means the liquid layer, which is in connected with the moving plate, is also moving at the same velocity u. Okay. And the fixed plate which is kept at the bottom and the layer of the liquid which is in contact with the fixed plate, we assume that is in stagnant state itself. And in between liquid layers, how they behave is very important. Once I move the plate in the forward direction, so it may behave like linear direction or it may behave like a non-linear direction. It depends on the liquids. So here, velocity disturbance, if you see, the layers which are in contact with the moving components, it may be a plate or it may be a rotor or it may be a circular ring, whatever. So those layer of liquid which is in contact with the moving parts will move with respect to the same velocity of the plate which is moving. And at the bottom, wherever the liquid layers, the oil which is in contact with the stagnant components, they are also moving at a zero velocity. So that is shown with these profiles. And this profile depends on the different liquids, like linear movement or it may be a non-linear, depends. Okay. Have you understood this topic before going to the derivation? What exactly in the experiment they are considering? Have you understood? Okay. In the next class, we'll take the same topic. We'll derive one small equation, how viscosity is related with respect to these two moving bodies. One is stagnant, one is moving. And how the liquid will behave in between these two plates, theoretically. And with respect to that, we'll discuss about the different fluids with viscosities and how to find out the at what velocity it is moving, at what distance if you maintain both the plates, then how the viscosity of the fluid can be varied. So these all things we'll discuss in the next class. Okay. So I'll stop this session here. We'll take the topic in the next class. Thank you.